Thank you all for joining us again for potentially the third time in the last week. I won't spend too much time on kind of the introductory material because you've probably all heard it before. The software I'm going to talk about today and give you a quick demo of is our BEES software, which is looking at whole building sustainability and kind of looking at the trade-offs that you have to give with regards to energy efficiency, energy, life cycle cost, and life cycle impact assessment. And so just some quick background on me. I am an economist, but I do a lot of work related to whole building energy modeling, life cycle assessment, of course. So I have a background in a range of kind of the necessary topics to discuss sustainability for whole buildings. And the main project that I oversee is Metrics and Tools for Sustainable Buildings. The name really says it all. We're basically trying to measure sustainability using science-based metrics, and we use a life cycle approach. So we use life cycle costing, life cycle impact assessment, and we've started to incorporate some other metrics, really looking at indoor environmental quality. And we're really looking at a broad range of stakeholders, and we're trying to educate and inform to help them make better decisions with regards to sustainable choices. And so we really target a range of groups, whether it's government agencies, industry groups, academia, general public. So it's kind of a wide, a really broad audience. We do publish a lot, but what I'm going to focus on today is a software tool, specifically BEES. And to measure whole building sustainability, it really takes a kind of really complex approach relative to individual products, which some of you may have seen the demo of just a couple of days ago. And so you're looking at the economic and environmental performance, but you also have to look at the performance of the building itself in terms of the occupants to make sure that the indoor environmental quality is good, to make sure the building's high performing. And so BEES was developed based on the BEES framework, and the first release was in 2014, and then we released one every year since. And so we're now on version 3.1, which you'll see a demo of shortly. And we've got a version 4 that's planned for next year. And really the target audience for this is really higher level decision makers. It's really standard and code and policy oriented to allow for these decision makers to look at the trade-offs in terms of improving energy efficiency in buildings. And similar to the BEES sustainability framework, the BEES framework's looking at a combination of economic and environmental performance. In terms of the economics, we're looking at life cycle costing. So you look at all the costs associated with the building, all the first costs, any future costs, whether it's operating energy, whether it's maintenance or repair and replacement, as well as any value of the building at the end of the study period you're looking at. And then with regards to the environmental impacts, we're using a life cycle impact assessment approach where you need to aggregate all the environmental flows up from their individual flows up to impact categories. And you'll be able to see some results at this level, but we also allow for a weighted normalized average to be created. Basically take the environmental impact category flows, normalize them by the flows for the entire US for a given year, and then you do a weighted average of those normalized values based on how important each of these impact categories are for you. And I mentioned that whole buildings are a lot more complicated than individual building products. That's really particularly on the life cycle assessment side, because to do a process-based kind of bottom-up approach for every single product in a building is really impossible. There's thousands of products in a building. It'd just be way too time-consuming, and it'd just be way too costly to do. And so instead of doing the process-based LCA for every single product and aggregating all those products up for the entire building. We have to look at some alternative approaches, which one approach would do it using a top-down approach for using environmental input-output tables, which is it's based on the economic supply chain, and then there's been environmental flows associated with those. And then we actually have those further broken down by building type. So whether it's a single-family dwelling or an office building or a school, we actually have essentially the average emissions for constructing that particular building type. And I refer to this as a fuzzy number because it's really an industry average as opposed to the exact flows associated with a particular action. If you're improving energy efficiency, if you change the window design, this industry average isn't necessarily going to be a great representative of the detailed results for that. So what we do is we take a combination of the process-based data and the IO data to come up with the best kind of picture possible. So optimally, you do the LCA from a bottom-up approach, get every single detail of the picture. That's not really possible. So really what happens is you get really detailed data on maybe the solar PV system or the windows or the wall assembly construction, but then you're missing the rest of the picture. And so you can't really determine what the magnitude impact of those changes are relative to the building as a whole. But if you just use the IO data, you get the full picture, but it's fuzzy. You don't get all the little details associated with it. And so what we do is we take a hybrid approach where we use the process-based data for all the building components that we're really interested in, that really have an impact on energy efficiency, and then we use the IO data to kind of fill in the blanks everywhere else. So you get the best picture possible given the data available. And so this hybrid approach for a whole building, what we do is we essentially define kind of a least efficient baseline building design and use the IO tables to calculate the emissions associated with that baseline building. And then for the components that we're changing to improve the energy efficiency, we use process-based data. And so whether that's adding insulation, or putting in more efficient windows or more efficient heating and cooling equipment, we're able to get kind of the best picture possible using the data that is available. And so the data sources that we have to combine together it's a combination of energy modeling and building component characteristics with data on the cost of construction, as well as energy and future costs associated with maintaining a building, and then combining that with the process and IO LCA data. And so based on the building design, we can estimate the cost of constructing that building and the flows associated with that construction. And then we take the whole building energy model, which we use Energy Plus. And so it's a software developed by DOE. It's publicly available to use. It's kind of really one of the most powerful tools out there for whole building modeling. And so we use that to estimate the energy consumption for the building, and then the cost data for energy for those particular location that you're at. And we can calculate the operating energy costs over the study period you're looking at. And we have LCI data for particular locations as well related to electricity consumption. So it's customized to calculate the energy-related flows related to that operating energy consumption. You also have to take into account any maintenance, repair, and replacement, as well as any value of the building at the end of the study period, and all the flows associated with those future activities. And then you aggregate all the costs up in terms of their present value, aggregate all the environmental flows up, and you're able to get your life cycle assessment. And then I mentioned a concern about the indoor environmental quality at this point for one of the databases, which is the demo I'll give will include this, is two different indoor environmental quality metrics. One is thermal comfort, so whether the occupants are comfortable, and then indoor air quality. So we have a proxy for that I'll get into later. So by combining these four aspects, we're able to calculate sustainability performance for a whole building over its life cycle, based on the changes in energy efficiency that are being considered. And so there's 3 databases that we've developed. The first 2, which were released in the first 2 versions of the tool, one for commercial buildings, one for residential buildings, are really standards and codes based. And so these are based on what states have adopted in the past for their state energy codes for building construction. And they're either for ASHRAE 90.1, which is the basis for most commercial building codes. And then for residential, it's the International Energy Conservation Code for residential buildings. And so what we've done is we have a range of prototypes for both for commercial and residential, and we model these across 228 cities, across these different editions of these standards and codes, and then we allow you to make those comparisons. And so all this data is pre-processed. When you make your selections, it's all real time and an immediate response with regards to what you're looking at. And I always kind of think of that as a mile wide but an inch deep analysis. So you're not really getting into incremental changes of energy efficiency performance. You're looking at a suite of changes that occur, some combination of insulation or air leakage rates and equipment improvements in terms of their efficiency. So what we did with the third database is we're actually basing it on the NIST Net Zero Energy Residential Test Facility. So this is an actual facility. You can see the picture on the left. The house, it's actually here. It's being operated. We've been able to validate the whole building energy model based on the actual performance of the home. And then we've used that model as a basis to do a lot of incremental what-if analysis. And we really look at all the different potential building component characteristics from a range of the different IECC editions, as well as the actual components in the net energy house and incremental options in between those two. So we wanted to see if there's incremental benefits of those additional energy efficiency incorporations. And so once you account for all the alternative assumptions that we allow for users to select the best match of their case, there's actually over 75 million records that you're searching through. And once again, these are all pre-processed, so the data is already there. All it's doing is it's searching through the database to find the data that you want to look at. So with that, let's go ahead and move to the demo. And so here's the main page, the home page for birds. And you can see each of the 3 databases here are accessible. You just click Start Analysis to go to that particular database. There's a brief explanation of what BIRDS is, its purpose, as well as how it's evolved over time, what's been included in each of the new versions, and kind of the plan forward of what's going to be included in the future. And then on the left-hand side, we try to keep any news or publications there linked, so you can easily find, what are the new publications that have come out associated with our BIRDS analysis and so forth. And you can get links related to whether it's the Net Energy House that you want to link to, whether it's the BEES software or our office. So the analysis that can be done for the residential and commercial buildings databases is also available in the low energy residential database, but there's also some additional features that we've added over the last year that I want to touch on. So we'll actually do a demo using the low energy residential database interface. And so once you click on which database you want to analyze, you'll see that there's just kind of an overview, gives you a brief description of what BIRDS is and what you can do with it. We've also included a description of what the particular database includes and the changes that have been made. So you can see in bold that these are the changes that we've added in this newest version. So version 3.1 added in an exterior wall finish option, added in the indoor environmental quality metrics, and it incorporated some additional graphing features and data visualization options that didn't exist before. And so you'll see that when I walk through those momentarily. And you actually, at any point in time, you can come back to this home page here in the top right, or you can download the documentation or a tutorial that can help you walk through this, as well as an FAQ that'll be a living document that, as we get feedback from users, will incorporate questions that people have asked that help to clarify things if there's any uncertainty there. So, once you kind of introduce yourself to birds, then you can move on to the actual steps for the analysis. And there's really only 4 steps. They're relatively straightforward. The first step is you have to choose what your baseline assumptions are. And so there's a list of drop-down menus that you can select from. And if you have any questions at all, these information icons can be clicked on. It'll give you a brief description of each of the options. If you need further explanation, you can go to the documentation for further details if you have any questions. So we're trying to be as user-friendly as possible, give them all the information they need to use it. So in this case, at this point, for this database, we only have the NIST Net Zero Energy Residential Test Facility, although as with all of these options, we've designed it to handle additions in the future. So if we develop another model for say a 1-story house, we could include that in relatively easily. The tool itself could then automatically display those results. Similarly, all of the analysis up to date has been for Gaithersburg, Maryland, because that's where the house is located. And once again, that's something that we can change. We can run this model in a different location in the future if we feel that that's a good addition to the tool. And then there's the discount rate, which is essentially your alternative investment rate of return that you'd get. So you can choose a more conservative or a more aggressive approach for government bonds. Kind of an expected rate of return is really a low risk. So that's kind of the 3% return versus an 8%, which is close to the long run real return of equities. So you can choose that based on what where you would put the money if you weren't putting into additional energy efficiency into a home. And then there's also financing options, whether you want to basically purchase the house 100% up front. The first financing option we've included is actually an 80-20 loan where you put 20% down. And the reasoning for selecting that one as the first financing option is we don't have to worry about mortgage insurance. It makes the analysis a little bit cleaner and easier to do. But in the future, we'd like to expand that to include some other options as well. And then you can select construction quality. And so what this is capturing is the fact that interior finishes can add $50,000 to $100,000 to a home, depending on how high end you go. And so we wanted to give the option to include that in for the cost analysis side. So we'll just choose average finishes for now. And then also we've incorporated in the option for either siding or brick veneer. I would note that at the moment we're modeling wood siding, but with regards to the actual energy performance, whether it's wood siding, vinyl siding, or cement board, the relative thermal performance impact is so minimal that it's simplest to just assume that the wood siding represents all those different siding options, because the insulation component is actually separate from this finish option selection. And I'll talk a little bit about the wall insulation here momentarily. And then the final assumption you have to select is the study period. So this is essentially your investment time horizon. If you're looking at a mortgage, a 30-year mortgage, maybe you want to look over that entire 30 years to see what the benefits are. Maybe you only expect to be in a home for 15, so maybe you'd select that as your option. So for now, let's assume a 30-year study period that matches up with the length of the time of the mortgage. So once you've made those selections, you then actually have to select what you're assuming as your baseline building. And we try to make this as simple as possible, allowing somebody to essentially select the design that meets current state energy code. So you can see it's actually auto-populated to the 2012-2015 IECC option. And I would note that the reason why these two are grouped together is that the requirements for each of these 10 components here are the same for both editions. So there's a big jump from the 2009 to 2012 edition of IECC in terms of the energy performance. And then from 2012 to 2015, there was almost no changes but particularly in the climate zone for Maryland, there was zero change for these options. So those are grouped together. So this was that automatically selected the 2015 IECC because that's what Maryland uses as its state energy code. And you can see here also, it's actually telling you that your design is based on an IECC edition. If you want to change this, you can, so if I change the wall, you see this automatically updates to show you that you're no longer based on the IECC edition. You've made some changes to make some custom design that you want to use as your baseline. But for simplicity, let's assume that we want to use our baseline as the Maryland Code Compliant design, which is the 2015 IECC. So we select that. Everything down the rest of the way is auto-populated based on that. So once you've made that selection, then you have to look at what comparisons you want to make. And so in this case, you're looking at, okay, well, if we change the energy efficiency performance of the building, you have to decide what options you want to consider. And so you can either select different editions of the IECC, whether, in this case, you'd be looking at older editions, or you can select a custom or set of custom building alternatives to compare. So for this first example, let's just look at the IECC editions. So this is the capabilities that you would see in the other two databases as well. So in this case, I selected both the 2006 and 2009 edition options. So then in step 3, you have to select your environmental preferences. So I mentioned the weighted normalized average. That's what this is specifying, is how you're going to do that weighting. We give some predefined options, whether it's, for example, the BEES stakeholder panel, which was developed here at NIST, bring in a group of stakeholders that basically we use to not to get too technical, but an analytical hierarchy process, which is all standards based from ASTM to develop these weights. There's one based on the EPA Advisory Board analysis in the past. And then there's also, you can also customize your own design. So as long as your numbers add up to 100, you'll actually see my weights pop up as an option. But for simplicity, let's just go with the BEES stakeholder panel option. So then once you've selected the way you want to weight your environmental preferences, then you can move on to step 4. And you can see the data is currently loading. It didn't take very long because there's only a few selections that were made. And then you can download the data. So it's not possible for us to incorporate all the graphing options that you may want, but we've included some that kind of highlight the key results. But if you want to do more with the data, you can download it and manipulate it the way you'd like in Excel. So all 3 databases have these bar graph options. What this allows you to do is look at any of the metrics that were discussed earlier. So let's just select operating energy. And then you can compare across, in this specific example, looking at the different IECC editions. But you could also look to see if you've selected a number of wall options. You look at the baseline design and then just change that wall option and see how the incremental benefits change. But in our case, since we selected the 3 IECC editions, let's compare across those 3. And then and there's a range of units that you can use for the metric. And so let's just assume total kilowatt hours over the study period. And so once you've clicked view, in a second it'll pop up. And so you can see you're looking at operating energy for the NIST Energy House in Gaithersburg, Maryland for the 30-year study period. And the 2015 edition of the IECC leads to lower overall energy consumption. And you can see that the kind of the baseline line graph here and relative to the 2006 and 2009 editions are much higher. And down underneath, you can see all the units that were available in the selection option above. So you can actually see the change in kilowatt hours per year, where you actually are saving for relative to the 2009 edition. The 2015 IECC edition leads to almost 9,000 kilowatt hours of savings over or per year, And then similarly for the 2006 edition, was actually even higher, is about 9,300 kilowatt hours. So that's the graphing capabilities available in all three databases. But what I want to get to now is actually looking at more incremental analysis and then show you these other three tabs and how those can be used. So let's go back to step 2. And instead of looking at the IECC editions, we'll unclick those. And then we want to look at selecting alternatives to look at relative to the baseline. And so here you can actually see all the different options that can be selected. And so whatever you select, you'll get the baseline design and all the incremental changes from the different combinations of your options that you select. And so just to walk through these alternatives real quick, with regards to the wall assembly design, you're essentially looking at changing in the type of framing and the amount of insulation. In the attic space, you're actually looking at where you put the insulation as well as how much insulation is there. The windows, you're looking at changes in the thermal performance and the heat gain that it allows. Foundation, you're actually looking at the insulation for both the wall and the floor of the unfinished basement. For lighting, you're looking at how many of the fixtures are high efficiency. For the air leakage, it's essentially looking to see how much air goes into the building through all the little tiny cracks and crevices throughout the entire building design. And then you also got more efficient heating and cooling equipment, more efficient hot water heaters, and potential of incorporating a solar thermal system to help preheat your water, as well as solar photovoltaics. So those are put on the roof to produce electricity. So what I'm going to select as the alternative design is the net zero energy house design. And one other note too here is from left to right is the least efficient to most efficient options. So for the wall, if you're going from R13 in the cavity with 2x4 framing, the baseline actually uses R13 in the cavity plus R5 of rigid insulation on the outside of the house. There's another option where you're actually shifting to a 2x6 framing, so you have thicker walls, so you can fit more insulation in, so you can get to an R20. And then these last two options are adding rigid insulation on the outside of the wall to increase the thermal performance. And so, similar aspects related to the rest of the building design, but we don't have time to walk through all the characteristics. But so we'll select the far right option for each. And so what the tool is going to do is actually give us the net zero energy house design, the Maryland code compliant design, and all the incremental combinations of these that have been selected. So you're going to get a whole bunch of data points. We'll leave the environmental preferences the same, so we'll jump back to the results step, and you can see the data uploaded already, so you can download it. But what we've added is a summary table that gives you the information of some of what we consider key building designs that people might be interested in. So instead of you having to go through the data and figure out some of these points, we're trying to give you that information to start with. So you can see here you have, for point A, it's the baseline design. So that's the Maryland code compliant design. Point B is the design that leads to the lowest life cycle costs. So that's in terms of just purely economics. That's the one that you'd want to select based on your underlying assumptions. Point C is the design that leads to the most amount of energy savings for the same life cycle cost as the baseline design. And so basically that's somebody who's like, I'm willing to spend just as much money as I would to meet code, but I want to get as much energy savings as I can for that same cost. Maybe you're interested in trying to reach net zero, so you want to produce as much energy as you consume in a year. And so point D is that point where it's the net zero design that leads to, or that's done that reaches net zero at the lowest life cycle cost. And then point E is the design out of the ones that you selected that leads to the lowest amount of energy consumption regardless of cost. And then point F is the design that leads to the lowest environmental impact score. So that weighted normalized average of your environmental impact categories. This is the design that leads to that being the lowest possible. So the smallest environmental footprint. And so in some cases, these designs will be the same. In some cases, they'll be different depending on what you select in terms of your alternatives that you want to compare. And then the table below that actually gives you the key results for those key building designs. And so it gives you information related to costs, to the energy performance, to the environmental performance, as well as those indoor environmental quality metrics. And just for an example, you can see that the design that leads to the lowest life cycle cost is about 24% more efficient than the baseline design. But for the same cost as that baseline design, you can actually get past net zero. You can actually be a net excess producer of electricity and do so at the same cost as the baseline design over the 30-year life cycle that you're looking at. So we gave you the results in a table, but we also wanted to be able to allow people to see this information visually, as well as look at all the points at which you selected. And so we created some scatter plots that essentially allow you to compare the economics to the energy savings. And so this first graph for the x-axis, you're looking at the percent energy savings. So at 100% energy savings, you reach net zero performance. So you're essentially consuming nothing in terms of net because you produce as much as you consume for the year. And on the y-axis, you have the total life cycle costs. And so the trend that you can see here is that initially costs go down, and then at some point they start to trend back up to actually further increase energy savings. And you do have some options with the graphing here. You can only select just your key points in yellow. You can actually populate and show all of the points that you selected. One other thing too is if you're not just looking at the life cycle costs, some people are really concerned about their upfront costs. And so that's what this initial investment cost versus energy savings graph is for. So it actually can show you what essentially your down payment is upfront. So you can see the lowest cost, just under $69,000, and to get all the way up to net zero, you're over $78,000. So there is some upfront cost, but the energy savings more than offsets that over time. So moving on, the radial charts, and so this is another way to visually show results. Here's the key metrics and their relative change versus the baseline. So you can actually minimize which ones you look at. So let's just start with the baseline design. So as you can see, for the baseline, there's a 0% change relative to the baseline because it's a change versus itself. And let's add point B. And what you can see is there's some reduction. So you can see the 23% reduction in energy consumption. You also see reductions in the environmental impacts. But you do see this big increase in the number of hours at which the CO2 level is above 750 parts per million. And this is just a proxy for indoor air quality. So one, don't be too concerned about the percentage change because it's relative to a really small number of hours at which these parts per million were this high. But what it's really showing is that there's a trade-off between comfort, which is improved by about 11%, and then you've got this increase in terms of the hours at which the indoor air quality may not be as high a quality as you'd like. So by improving energy efficiency, making the building tighter so you have less infiltration leads to a concern for pollutants in the air inside the house. And so that's something you have to think about when it comes to designing these low energy homes. And then, so moving on to the next point. So this is the design that leads to the greatest amount of energy savings for the same cost as the baseline design. And you can see you can get past net zero for energy consumption you get reductions in the environmental impact score and climate change. The number of hours uncomfortable gets even better, so it's dropped by 25% this time. So you're getting energy savings, you're getting a design that's more comfortable to the occupants, but you still have to think about the concern with regards to the indoor air quality. So moving on to the results that are probably of most interest to the group on this call, here's the impact categories relative to the baseline. So this is percentage of the baseline. So at 100% is the baseline values. So when you go to the minimum life cycle cost design, so the one that saves you the most money, you can see there's a trade-off. So you get reductions in energy use, in smog, in acidification, climate change, respiratory effects, non-cancer causing human health, but you do see some increases: ozone, ecotoxicity, water use. So what you have to add to the building to get the energy savings is actually increasing some of the environmental impacts. So you have to account for these trade-offs, and so that's where we're looking at here. And then, so now let's look at the design that gets you the most amount of energy savings for the same cost as the baseline design. And here you can see this quite a bit of change. Once again, you see reductions in a number of categories, but you also see increases in others. And the one that really pops out here is the ecotoxicity number. So the percentage number on the graph, it looks really large, but it's actually relatively comparable to the acidification, just in the reverse direction. So ecotoxicity goes up by about 450%, but acidification goes down, and it's only 21%. So it's basically a fifth of what it was versus 5 times what it was for ecotoxicity. So you have a similar magnitude change, just in opposite directions. So once again, you're looking at trade-offs. You have different by all the embodied emissions associated with materials. You have increases for some of the characteristics where you have decreases in others. So that's showing all the features that the tool allows, some really quick comparisons, and you can always download the data and do your own analysis. So at that, let's hop back to the presentation. So future capabilities of birds that we're looking at, we're actually currently working on version 4. We've we're going to break out the 2015 IECC and make it designed so 2018 is ready to incorporate whenever that comes out. We're currently updating the commercial buildings database, shifting over to using the DOE PNNL reference buildings, and to incorporate all the newer editions of ASHRAE 90.1. We're actually waiting on the public release of the 2016 edition of 90.1 energy models from them. And then moving beyond that, we designed the tool so we can easily update the current data. So all the code has been written to rerun everything based on new information, as well as to add to the database, so adding more options. Just for an example, if we get new LCIA data or we get new cost data, such as solar PV, which has dropped significantly just over the last year or two, those are things that we can change in the underlying source data tables, rerun the code, and generate these results in the matter of days or weeks, and then incorporate those into a new version, or just do an update of the underlying data. We can incorporate new additions for the standards and codes, as well as new metrics as we, so such as the indoor environmental quality metrics. If we can come up with new results for that, we can incorporate those for other pollutants other than CO2. We can also incorporate new options. One example is we're currently running and validating a database to expand the low energy residential database to include gas, space, and water heating, since that's actually the primary heating source for this area. So we wanted to include that as an option. But really, we're looking for user feedback. So if there's anybody that's using birds and has something that they'd like included or something that they think we could improve upon, we'd love to hear from them. You can just email me, and we can try to address those thoughts. One thing I also do want to mention briefly is that we are, at this point, everything's been predefined prototypes that have been rerun, pre-processed. So you can't do a custom building design. So we wanted to expand into that area, and we worked with NREL's OpenStudio team to develop a feature that goes into their tool that can actually do the same types of LCIA calculations, but do it with a custom building design. And we're trying to design it generic enough that it could actually work with other software, not just OpenStudio. And so here's just a brief visual of what we're doing with that. So if you look at OpenStudio, here's what the interface looks like. You basically drag and drop what's referred to as a measure. So it's based on energy efficiency measure is where the term came from. But really, it's just a way to manipulate the model. And so what it's doing is it'll grab information from the underlying model and from the results and send that information to us. And you can see on the right-hand side, there's a little bit of information the user has to input on their design. But then once they've input that information and they run the OpenStudio model, then the model is going to create a JSON file, basically a text file with information that gets sent to a web server. Our API is searching that web server for a file. As soon as the file hits it, we grab it, parse it, run the LCIA calculations, send an output file back, and then that file then goes to OpenStudio, and then you can visually see that in OpenStudio as a report. So you never have to leave the tool. You get all the same types of calculations, and actually in this case, we're probably even giving greater detail of the LCIA data than what we do in the BIRDS tool. Because this is more for people that really know what they're doing, really have a specific design they're interested in, and want to get into the details. Where the BIRDS tool is really designed for higher level decision making and informing users, as opposed to really allowing like an architect or a designer to create their own design and do the same types of calculations as they run their options. So at that, I can open it up to questions, comments, any feedback, and thank you all for joining.
Great, thanks, Josh. It looks like we have one question so far. If anyone has any other questions, please feel free to put them in the chat box, and we will have Josh answer them. So the one question is there an opportunity to add other environmental measures such as raw material consumption associated with building material input or waste generated?
So, I mean, that's something that we, I guess, could consider. That's the first time anyone's actually brought it up. So at this point, we've kind of stayed consistent with the impact categories that we've been looking at. But that's definitely something I can have discussions with my team and with our LCA practitioner as to what that might take to include. So the person that asked the question, please email me with a little bit more detail. And then I'll take a look at it and see what we can do.
Great. Well, Josh, thank you so much for this fabulous presentation. As I mentioned to everyone, we will be posting it on ACLCA's YouTube channel, as well as sending out the video to everyone who's attended. So thanks again, and have a wonderful afternoon.